In this video, I will be explaining the physics concepts behind my pop-up boat using various concepts from both Physics 1 and 2. In our scenario, the pop-up boat remained above the water. Why is this, you may ask? This is due to the difference in densities of the two objects, as well as the buoyant forces in action. In physics, density is defined as the total mass of that substance divided by the total volume occupied by that substance. The equation to calculate density would be the mass in kilograms divided by the volume of the object in meters cubed, making the units kilograms per meters cubed, which is represented by the Greek letter rho. Compared to the density of water, if an object had a greater density, then it would sink underneath the water, while if an object had a smaller density, it would rest above. Because of our foam insulation boat having a smaller magnitude of density than the water it was resting in, it remained afloat. Another explanation for why our boat floated was the aforementioned buoyant forces between the water and the boat. By definition, buoyancy or buoyant force is a force exerted on an object that is wholly or partly immersed in a fluid. Buoyancy is caused by differences in pressure acting on opposite sides of an object immersed in a static fluid. Since there is a difference in the pressure between the atmosphere and the water below, there is a buoyant force in play. In order to calculate a buoyant force, we must use the equation shown on the screen given to us by Archimedes' principle, which states that the buoyant force on a submerged object is equal to the weight of the liquid displaced by the object. Due to multiplying the density of the liquid displaced, the volume displaced, and gravity, the units of measure would come out to be Newton. The concept of heat transfer is all around us, in our buildings, in our clothing, and in our vehicles. Heat transfer is also present in the pop-up boat, as seen in the candle transferring heat to the water and air within the engine. In all, this concept is what will cause the boats to move. The equation for this is seen on the screen, with Q representing the energy transferred to a system by heating, delta lowercase c the time in which a system is heated, K the thermal conductivity of the medium, A the area of the medium, delta capital T the temperature, and L the thickness of the medium. In testing the type of engine we were going to use for the boat, we discovered a key difference, the part of the can that was used. Using the bottom of the can for one design, we had a difficult time heating the water, let alone getting the engine to work due to our smaller heating source. However, when we used the circumference of the side section of the can, not only did it heat up quicker, but it moved faster. This is all due to the simple difference in the thickness of the can, as well as the conductivity of each part. In order to make the boat move, the can, which serves as the engine, must encounter 4 stages. We can examine these 4 stages by looking at pressure versus volume diagrams in the equation for the change in internal energy. The equation, delta U, is the change in internal energy, Q is the energy added to the system, and W is the work done on the system. The first process is isochoric, meaning that the volume is constant. This is represented by a vertical line on the P versus T graph. Along the line, the wick of the candle is first lit, and the can has no work being done on it or by it, as it is not moving and is just getting heated by the candle. We know that the pressure inside the can increases due to an increase in temperature, since they are directly proportional. In addition, the temperature is directly related to the change in internal energy, which means that this increase in temperature would make this change of internal energy positive. Now, looking at the remainder of the equation, we can assume that the energy added to the system is positive due to no work being done, as well as the positive change in internal energy. The second process is isobaric, meaning that the pressure within the system is constant. This is represented by the horizontal line on the P versus V graph. At this stage, the engine will pop outwards, increasing the volume of the system, and overall making the work done on the system negative, as the motion is going against the force applied. Since pressure is constant and volume is increasing, temperature will increase as well, meaning that the change of internal energy is positive. Due to having 2 of the variables of the equation for the change in internal energy, with work being negative and overall change in internal energy being positive, we can deduce that the energy added to the system is positive as well. The third process that the can endures is isochoric. However, this time the pressure of the can decreases. This will create a vertical line on the P versus V graph. During this stage, the steam within the can pushes the water out of the straws to thrust the boat forwards, which results in a decrease in pressure within the can without any change in the shape of the can. Due to the identical shape of the can, we can say that there has been 0 work done, which brings us to figure out the change in internal energy. Seeing as the only thing that is left in the can is steam, we are continuing to add heat to it via heating by the candle. This means that the change in internal energy is positive, with the increase in temperature and energy added to the system would also be positive. The fourth and final process that occurs in the can is isobaric, with the volume of the can decreasing. This can also be viewed as a horizontal line on the P versus V graph. During this final step, the boat pops for the second time. Cold water will rush into the engine through the straws due to the difference of the high pressure in the water to the low pressure within the can, causing the shape of the can to return normal once again. The cold water brings a decrease in the temperature of the system, which causes the change in internal energy to be negative. This also shows how energy is removed from the system due to the decrease in temperature, as well as the decrease in the kinetic energy of the molecules. Finally, due to the volume of the can decreasing, the work will be positive, as the motion of the can is moving in the direction of the force. As stated by Sir Isaac Newton in his first law of motion, an object at rest will remain at rest, and an object in motion will remain in motion with a constant velocity unless acted on by an outside force. The law can be applied to the pop-up boat as a consistent release of water thrusts the boat forward when the candle is lit, but when the candle is out, the boat is carried forward by its momentum. Momentum can be defined as a property or tendency of a moving object to continue moving. An equation representing the concept of momentum is displayed, where p is the momentum vector, m is the mass of the object, and v is the velocity vector of the object. Imagine Newton's cradle. The velocity of the balls in the cradle will be conserved unless interrupted by an outside source.